Welcome back to the Deep Dive. You've come to the right place if you need a reliable shortcut to being deeply informed. Today, we're kicking off a pretty massive project. We're going to translate the entire official ISTQB Certified Tester Foundation Level syllabus, that's version 4.0.1, into exam-ready auditory knowledge. This is episode 1 of your comprehensive prep course.
It is, and our mission today is foundational, really. We're diving deep into the syllabus introduction first, so understanding the exam structure, the cognitive levels, all that baseline terminology. Then we jump straight into a full exploration of Chapter 1, fundamentals of testing. So if you're aiming for that CTFL qualification, maybe you're a dedicated tester, a developer, even a project manager or a product owner, you need to speak the language of quality. This session is, well, it's indispensable.
Exactly, and we're targeting depth here, not just rattling off definitions. Chapter 1 is the bedrock, and we need to lock in all the K1 objectives. That's the recall and recognition stuff. But crucially, we have to master the K2 objectives. K2, that requires real understanding, right? The ability to, explain, differentiate, give examples of why things are the way they are.
That's it.
I mean, most of the tricky multiple choice questions on the exam, they really lean on that K2 understanding, don't they?
They absolutely do. And, understanding that cognitive level really helps you prioritize how you study.
Right.
K1 is, well, it's pure memory work. Can you list the 9 test objectives? Can you recall what defect means? Those are the easier points to get, but you have to be precise.
And K2 is where the thinking really comes in. It's about using the vocabulary. Like, can you explain the actual difference between quality assurance and quality control on a real project?
Right.
Or can you look at a scenario and tell me if it's verification or validation? That's what we're building today. We are building the mindset of a really well-informed tester.
And while Chapter 1 is almost all K1 and K2, later on we will get to K3, which is application. K3 means you actually have to do something, apply a technique, maybe calculate something, prepare a report. But you can't apply anything until you really, truly grasp these fundamentals. So let's start at the very beginning. Let's ask the question. What is testing, according to the ISTQB?
Let's do it. So when most people think about testing, I think they imagine that last week before a release, just frantic clicking and chaos. But the formal definition is much broader than that, isn't it?
It is, and this is a really critical distinction for the exam. Testing is officially a set of activities designed to discover defects and evaluate the quality of software work products. And those work products, it could be requirements, designs, code, even user manuals. We call them all collectively the test objects.
So the key thing here is that testing is not just running the software.
Absolutely not. The syllabus really emphasizes this. Testing is an umbrella term. It includes planning, analysis, design, implementation, and then execution. If you think testing only happens at the end when you run the code, you are missing, maybe 75% of the whole effort. It has to align with the entire development lifecycle.
That broad scope, it immediately brings up the first major split we need to talk about: dynamic testing versus static testing.
And this is a classic K2 differentiation area. So dynamic testing is what most people picture. It involves actually executing the software. You run the code on a machine, you interact with it, you check the results against what you expected.
Okay, so dynamic means the software is running.
Exactly. And static testing is the complete opposite. It does not involve execution. Think of it more as intellectual analysis. You're reviewing, reading, analyzing documents and source code without ever running the system. This includes things people do, like code reviews or walkthroughs, but also automated tools that check code for standards without running it.
So static testing is really the ultimate shift-left activity. You can do it on the requirements document before anyone has written a single line of code.
You've got it. Which, ties right back to that principle that finding things early saves money.
Right.
And speaking of foundational K2 concepts, we absolutely have to differentiate 2 terms that get mixed up all the time: verification and validation. This is a must-know for the exam.
Okay, let's unpack this. I've seen senior people get this wrong.
Let's start with verification. Verification is all about checking if the system meets its specified requirements. The question it asks is, are we building the system right? We're looking inward at the documents, at the product itself. Does the design match the architecture? Does the code follow the spec?
So verification is all about compliance with the internal blueprint.
Precisely. Now, validation shifts the focus completely outward, towards the end user, the business, the stakeholders. Validation checks if the system meets the user's actual needs and expectations in their real environment. So the question for validation is, are we building the right system? You might have built the system perfectly to the specification, which is great verification, But if the user still can't do their job with it, you've completely failed validation.
I think an analogy helps here. Verification is making sure the light switch is wired correctly, according to the blueprint. Validation is making sure that light switch is actually on the wall where the user needs it, not, hidden behind a bookshelf.
That's a perfect analogy. You absolutely need both. Verification without validation gets you a technically perfect product nobody wants.
And validation without verification gives you a product that seems to work, but it's probably buggy, unstable, and impossible to maintain. Successful quality means doing both.
Exactly.
Okay, so we've defined the scope. Now let's look at the goals. The syllabus says we need to identify 9 core objectives of testing. This feels like a classic K-1 recall list.
It is, but instead of just listing them, let's try to group them. It'll make them much easier to remember, especially for an audio course like this.
Good idea.
We can break the 9 objectives into, say, 3 groups: quality evaluation, compliance and detection, and stakeholder communication.
Okay, I like that. Let's start with quality evaluation.
Okay, group 1, quality evaluation. These 3 are all about measuring the state of the product. First, evaluating work products. So that's requirements, designs, code. We test documents, not just the running software. Second, building confidence in the quality of the test object. When tests pass, trust goes up. And third, reducing the risk level of inadequate quality. Testing is fundamentally a risk mitigation strategy.
Right. So those 3 are about assessing the product's value and its safety. What's in the next group? Compliance and detection.
Group 2, compliance and detection. This is about finding problems and meeting external rules. So number 4 is the one everyone knows: causing failures and finding defects. This is the classic bug hunt. 5 is verifying fulfillment of specified requirements, checking things off the list. And number 6 is verifying compliance with contractual, legal, or regulatory requirements. This is huge and feels like finance or medicine.
Okay, makes sense. And the last group. How does testing serve the wider organization?
Group 3, communication and fulfillment. This is how testing connects back to the business. So number 7, providing information to stakeholders for informed decisions. The classic one is, should we release? Testing provides the data for that answer. 8 is validating that the object is complete and works as stakeholders expect. This links right back to what we just said about verification and validation.
Right.
And finally, number 9, ensuring required coverage of a test object. For example, proving that we've tested 90% of the requirements or all the high-risk areas.
Wow, that list really shows how complex the role is. It's not just a technical job. It's compliance, risk management, and communication.
And you have to remember, these objectives are not fixed. Which one you prioritize depends completely on the context. If you're testing an airplane software, compliance is probably number 1. If you're rushing a new feature to market, maybe risk reduction and providing information for a quick release decision are key. The context is everything.
Let's move to another key K2 distinction. One that gets blurry, especially on teams where developers also test. Testing versus debugging.
Yes, this separation is philosophically very important for the exam. In short, testing finds the problem. It identifies a failure or a defect. Debugging is the activity of diagnosing the cause of that failure and then fixing the underlying defect.
So testing is debugging is the how to fix it.
You've got it.
Let's walk through the flow for dynamic testing. When you're actually running the code, what happens?
Right. So your test execution triggers a failure. The system doesn't do what it's supposed to do. That failure is seen, it's reported. Then the developer, or sometimes the tester, starts the debugging process.
And debugging itself isn't just one step, is it?
No, it's really 3 steps. First is reproduction. Can you reliably make it happen again? Second is diagnosis, using tools and logic to trace that failure back to the defect, the actual flawed line of code. And third, obviously, is fixing the defect by changing the code.
And after the fix, the process isn't over. We have to do more testing. Why?
Because fixing one thing so often breaks something else. So after a fix, you immediately perform 2 types of testing. First is confirmation testing, or retesting. You just want to confirm that the fix actually solved the original problem. The test that was failing should now pass.
Okay, that makes sense. Check your work.
And second, and this is arguably more critical, is regression testing. This is to make sure that your code change didn't accidentally break anything else in other parts of the system that were working just fine before. It's insurance against side effects.
That difference between confirmation and regression testing, that feels like a very high-value K2 concept for the exam.
It is. Confirmation asks, did we fix the bug? Regression asks, did the fix create any new bugs?
Right. Now, what about static testing? How is that flow different? if you find a typo in a requirements document during a review?
Well, since we never executed any code, there was no failure. We found the defect directly in the work product.
So you just fix it.
You just fix it. The static testing flow only requires the removal of the defect. There's usually no reproduction or diagnosis phase because the review directly pointed to the problem. It's one of the big reasons static testing is so efficient.
Okay, so we've defined what testing is. Now let's tackle the big question. Why is it so necessary? This seems to be about justifying our jobs, really.
It is. This section is all about testing's value proposition. I mean, we've all seen headlines about software failures costing millions, or even worse. Testing reduces that risk. It helps make sure we meet our goals for scope, time, quality, and budget.
Let's start with the one that always gets management's attention. Money.
Contribution number 1. Testing provides a cost-effective way to detect defects. There's this exponential cost curve. A defect you find in the requirements phase might take an hour to fix. A defect you find in system testing is expensive. But that same defect found by a customer after release, it can be absolutely catastrophic. Early testing saves huge amounts of money.
It's also about accountability, right? Giving people a real snapshot of where things stand.
That's contribution number 2. Testing provides a direct evaluation of quality throughout the project. This helps managers make decisions. A test report gives them objective data to decide, are we ready for the next phase, or can we release this? It replaces developer optimism with hard facts.
You mentioned earlier that testing can act as a kind of proxy for the user. How does that work?
That's contribution number 3. Testers provide an indirect representation of users' needs. Look, it's just not practical or affordable to have a bunch of end users involved in every single meeting from day one. The test team steps into that role. They act as the user's advocate, making sure we're building the right product, not just the product that's written in the spec.
And the final reason testing is necessary is sometimes, well, you just don't have a choice.
Exactly. Contribution number 4. Testing is often required to meet contractual, legal, or regulatory standards. If you're building software for a medical device or a bank or anything that handles personal data, rigorous testing isn't just a good idea, it's the law. Skipping it can lead to massive fines or worse.
Okay, this is one of the most confused areas in the industry, which means it's probably a great area for exam questions. QA versus testing.
Yes. People use them interchangeably, but the syllabus draws a very clear line.
Let's get precise.
Okay. Testing is officially a form of quality control, or QC. It's a product-oriented corrective approach. The focus is on the thing you built, the software, the document, and finding problems after they've been put in there.
So QC is like an inspector on an assembly line, checking the car for dents at the end.
That's a perfect analogy. Now, quality assurance, or QA, is totally different. It is a process-oriented, preventative approach. QA isn't focused on the car at all. It's focused on the assembly line itself. The idea is if you build a great process, you'll naturally build great products and prevent the dents from happening in the first place.
So QA is about preventing the dents, while QC, or testing, is about finding the dents that still got through.
Exactly. And QA is everyone's job managers, developers, testers, everyone has to follow the process. But there's a link. The results from testing are vital feedback for QA. If your testing keeps finding the same type of defect over and over, QA's job is to step in and fix the process to stop that from happening again.
Okay, let's get into the critical cause and effect chain. The EDF chain, error, defect, failure. This is a huge K2 concept.
It is, because it's the foundation of all defect management. And it all starts with a person. An error, or a mistake, is a human action. It happens because of, pressure, tiredness, lack of training, or just the complexity of what you're working on. A developer makes an error writing code. A business analyst makes an error writing a requirement.
And the result of that human error is?
A defect. This is also called a fault or a bug. The defect is the actual flaw that's now in a work product. The error was the action. The defect is the result. So if the error was a typo in the code, the defect is the wrong code sitting in the file. And defects in early documents, like requirements, are what cause most of the later defects in the code.
Okay, so we have a defect in the code, and then we run that code.
And that's when a failure can happen. A failure is the observable event where the system doesn't do what it's supposed to. The system crashes, it gives the wrong answer, it's too slow. A failure only happens when the defective code is actually executed.
But not every defect causes a failure, right?
That's a key detail. Some defects will always cause a failure when you run them. But many are latent. They only cause a failure under very specific, maybe rare conditions. And, some defective code might never even get executed in the real world, so that defect never leads to a failure at all.
And that brings us to the last piece of the puzzle, the root cause.
The root cause is the fundamental reason why the human error happened in the first place. If a developer keeps making the same kind of error, the root cause might not be them. It might be that their deadlines are too tight or they're not getting proper training. That's the real problem you need to solve.
So a tester finds the failure and traces it to the defect. But a QA person or a good manager traces that all the way back to the root cause to prevent it from happening again.
Exactly. You fix the defect, but you eliminate the root cause. That's the heart of process improvement.
All right, now we get to the philosophical core of the whole thing, the 7 testing principles. These are like the universal laws of testing.
They are, and they are highly examinable. You need to be able to explain them, not just list them. Let's go through them one by one.
Okay, fire away. Principle 1.
Principle 1, testing shows the presence, not the absence of defects.
This is the one that keeps us humble. Even if we run a million tests and they all pass, we can't say the software is perfect.
Never. We can only show that defects are present. If we don't find any, all we've done is increase our confidence by reducing the probability of undiscovered defects. Proving correctness through testing is basically impossible.
Okay. Principle 2, exhaustive testing is impossible.
Right. I mean, think about a simple online form with just 5 fields. Even if each field only has 10 options, the number of combinations is 100,000. Add in different browsers, user roles, timing. The number becomes astronomical. You can't test everything.
So this is why we need to be smart about it.
It's the whole reason we have to use test techniques, prioritization, and especially risk-based testing. We have to focus our limited time and energy where it matters most.
Makes sense. Principle 3, early testing saves time and money.
This is the economic powerhouse of all the principles. It's the foundation of shift left. A defect found in a requirements document costs, say, $100 to fix. That same flaw, if it's found by a customer after release, could cost $100,000 in patches and lost reputation. So this principle mandates that we use both static and dynamic testing as early as we possibly can.
Okay, now for a statistical one. Principle 4, defects cluster together.
This is the Pareto principle, the 80-20 rule, applied to software.
Right. A small number of modules have most of the problems.
Yes, the data shows that a small number of components will contain the majority of the defects, or cause most of the failures. This is usually because they're more complex or they change more often. And knowing this is a huge input for risk-based testing, it tells you exactly where to focus your efforts.
Love it. Principle 5, tests wear out.
If you keep running the exact same tests over and over, eventually they stop finding new bugs.
It's like a pesticide, right? The bugs develop immunity.
That's a great way to put it. To find new issues, you have to modify your tests, write new ones, change the data. You have to keep looking in new places. Now, there's a nuance here for the exam. Repeating tests is absolutely essential for automated regression testing. You want to repeat those to make sure nothing broke. But for finding new defects, repetition is ineffective.
Got it. Principle 6, testing is context dependent.
This means there is no one-size-fits-all approach. You can't just have a standard test plan and apply it to every project. Testing an e-commerce website is completely different from testing the software in a pacemaker. The context, the risks, the technology, the industry dictates the entire strategy.
Okay, last one. And this feels important. Principle 7, absence of defects fallacy.
This brings us all the way back to validation.
So finding and fixing every single bug doesn't guarantee success. Why?
Because you might have perfectly built the wrong product. The fallacy is believing that if you meet every single specified requirement and have 0 known defects, you've succeeded. But if the system doesn't actually meet the user's needs or solve their business problem, it's still a failure. Fitness for purpose is the ultimate goal, not just technical perfection.
That is a fantastic summary. Let's do a quick recall. If a manager tells you to test every single possible input, which principle are they ignoring?
Principle 2, exhaustive testing is impossible.
If your company releases a product that meets the spec perfectly, but users hate it and leave for a competitor, which principle was violated?
Principle 7, the absence of defects fallacy. They focused on verification but failed at validation.
And if you notice that just 2 modules are responsible for almost all of your system crashes.
That's principle 4, defects cluster together. And it's telling you where to focus your regression testing next.
Okay, so testing isn't just random, it's a structured process. The syllabus breaks it down into 6 main activity groups.
Yeah.
We need to be able to explain what happens in each of these.
Right. And remember, Principle 6, context is everything. This process is just a framework. These activities might happen in a straight line in an old school model or all at once in parallel in an agile context.
Okay, so where do we start?
We start with 2 managerial groups. First is test planning.
Hmm.
This is where you define the whole approach. What are our objectives? What's in scope? What resources do we need? What are the risks? It's also where you define the entry criteria, when can we start testing, and the exit criteria, when are we done?
Okay, so you have a plan. Then management has to keep an eye on it.
Exactly. The second group is test monitoring and test control. These happen continuously. Monitoring is checking progress against the plan. Are we on schedule? How many bugs are we finding? Control is taking corrective action when monitoring shows you're off track. Maybe you have to change priorities, get more resources, or even reduce the SOAP.
Right, so those are the management activities. Now let's get into the technical stuff. The work of the tester. Where do they begin?
They begin with test analysis. This phase answers the question, what to test. The tester takes the test basis, that's the requirements or user stories, and analyzes it to identify testable features. The main output here is a list of test conditions, which are basically high-level things we need to check.
Okay, so we know what to test. Next is figuring out how we're going to test it.
And that is test design. This phase answers how to test. Here, you take those high-level test conditions and you elaborate them into detailed test cases. A test case has specific inputs, actions, and crucially expected results. This is also where you define the test data you'll need and the specific test environment setup.
So analysis is the big picture. Design is the detailed blueprint. What's next?
Next is test implementation. This is the preparation phase. You're turning that design into stuff you can actually run. So you're writing the step-by-step test procedures, maybe automating them into test scripts, organizing them into test suites, and building and verifying the actual test environment.
Let's pause on that environment part. The syllabus mentions things like stubs and drivers. Can you clarify what those are?
Good point. This is a great K2 clarification. When we test, sometimes parts of the system aren't ready yet, so we use simple pieces of code to simulate them. A stub is called by the component you're testing. It pretends to be a component that's below it. A driver calls the component you're testing, pretending to be a component above it. You might also use something more advanced, like service virtualization, to simulate a whole complex system, like a third-party payment gateway. All of that gets built during implementation.
Okay, so everything is ready. Now we actually run the tests.
Now we get to test execution. This is the part everyone thinks of as testing. You're running the tests according to the schedule, you're logging the results pass, fail, and you're comparing what actually happened to what you expected. If they don't match, you analyze the anomaly and report a failure.
And then finally the project wraps up.
Right. The last group is test completion. This happens at key milestones, like the end of a project. Here, you're archiving all your useful test materials, you're gathering lessons learned to feed back into the QA process, and you're writing the final test completion report for stakeholders.
We've hammered home that testing is context dependent. Let's be more specific. What are the key factors that force us to tailor that process?
It's a framework, not a recipe. And there are about 4 major groups of factors. First is the business context. So what industry are you in? Finance. Gaming. How critical is this system? Are there legal regulations we have to follow? Testing a life support system is going to be wildly different from testing an internal website.
Okay, business context. Then the technical side.
The technical context, what kind of software is it? A mobile app? Embedded firmware? What's the architecture? All of these technical details influence what tools you can use, whether you can automate, and what kind of testing is even possible.
And then there are the universal project constraints.
The classic trio: scope, time, and budget. The project constraints. If your time to market is super aggressive, you're probably going to have to accept more risk and lower your exit criteria. You just don't have time for perfection.
And lastly, the people in the organization.
The organizational factors. The company's culture, the skills of your team, and most importantly, the software development lifecycle SDLC model you're using. Testing in a rigid sequential model is fundamentally different from testing in a collaborative agile model. And that's actually the topic of our next entire deep dive.
Okay, let's talk about the artifacts, the documents. The exam keyword is testware. This is just a collective name for all the stuff we produce during the test process.
It is, and being able to map the testware to the right activity is a great test of your K2 understanding.
All right, let's try it. What testware comes out of test planning.
That's where you get the high-level management documents, the test plan, the schedule, the risk register, and your defined entry and exit criteria.
Okay. What about test analysis when we're figuring out what to test?
The main output there is your list of test conditions. You might also write defect reports here, but they'd be about defects in the requirements themselves, not the code.
And test design, where we figure out how to test.
That's where you create the detailed test cases, your test data requirements, and maybe test charters if you're doing exploratory testing.
And then the stuff we actually run comes from implementation and execution.
Right. Test implementation gives you the test procedures, the actual scripts, and any stubs or drivers you built. Test execution generates the runtime stuff, the test logs, and, of course, the defect reports about failures you found.
And to wrap it all up, test completion gives us
The test completion report and the documentation of lessons learned. If you can map those outputs to the activities, you're in great shape.
Let's talk about another exam keyword, traceability. This is all about creating links between, say, a requirement and the test case that covers it and the test result and any bugs found. Why is this so important?
It's the backbone of quality governance. Without it, you're flying blind. Its number one value is coverage evaluation. Traceability lets you prove that every requirement is covered by at least one test case. It turns, did we test everything, from a feeling into a measurable KPI.
So it answers the question, did we do what we said we would do?
Exactly. Its second value is risk evaluation. You can trace test results back to specific business risks. If all the tests for a high-priority risk are passing, you can say the residual risk in that area is now low.
What if the requirements change halfway through the project, which they always do?
That's the third value, impact analysis. It saves so much time. If a requirement changes, traceability instantly shows you every single test case that's linked to it. It tells you exactly what you need to update and rerun. And finally, it's all about reporting and governance. It makes your reports meaningful to stakeholders, and it's essential for passing any kind of audit.
Okay, let's compare the two main roles in testing, the test management role and the technical testing role.
Right. So the test management role has the strategic, big picture focus. They're responsible for the overall process, the team, the budget, the schedule. Their main activities are planning, monitoring, control, and completion.
They're the organizers. And the testing role is the technical engine.
The testing role has the hands-on tactical focus. They do the engineering work. Their world is analysis, design, implementation, and execution. They're the ones digging into the details, writing the cases, and finding the bugs.
So the key difference is mindset. Management is strategic budgets and timelines. Testing is tactical inputs and expected results.
That's a perfect way to put it. The testing role needs that deep curiosity and analytical skill. The management role needs strong communication and organizational skills. And on many modern teams, you'll see these roles blend, with developers and analysts also doing parts of the testing role.
Okay, moving on to the human side of things. The syllabus says testing is an intellectual activity. It takes more than just being good with computers. What are the essential skills?
You can really break them down into three buckets: technical skills, cognitive skills, and people skills. So technically, of course, you need testing knowledge. You have to know the techniques to be effective, and you need technical knowledge of the system you're testing to be efficient.
But the cognitive skills, the way you think, that's maybe what really separates a good tester from a great one.
I think so. You need analytical and critical thinking, and even creativity, to come up with test cases that nobody else would think of.
And think about the personal qualities: thoroughness, curiosity, attention to detail. You need that relentless curiosity to find the really tricky bugs.
And then the people skills. I've seen testers who are technical geniuses, but they're a liability because they can't communicate.
100%. Good communication skills, active listening, being a team player, they're all essential. You have to write clear bug reports, you have to explain risks to managers, and you have to discuss failures constructively with developers.
Let's focus on that constructive part. Why is that so important?
Because testers are often the bearers of bad news, and nobody likes to hear their baby is ugly. Developers can suffer from confirmation bias. They want to believe their code is good. So a tester has to report defects professionally and objectively. Focus on the facts of the failure, not on blame. The goal is to be seen as a helpful, supportive part of the team, not a destructive one.
The syllabus also brings up the whole team approach. This feels very modern, very agile. What do we need to know about it?
The core idea of the whole team approach is that quality is everyone's responsibility, not just the tester's job. Anyone on the team with the right skills can help with any task.
And the benefits of that.
The main advantages to recall are that it improves team dynamics and communication, and it creates synergy by using everyone's skills. A business analyst might write acceptance tests, a developer might perform a peer review. Everyone contributes to quality.
Finally, let's talk about independence. Why is it a good practice to have some distance between the person who wrote the code and the person who tests it?
It comes back to that cognitive bias again. An author is naturally biased. They see what they meant to build. An independent tester comes in with fresh eyes. They don't have the same assumptions, so they're much more effective at finding certain types of defects.
The syllabus lists 4 levels of this, from least to most independent.
Right, at the bottom, you have no independence. The developer tests their own code. A step up is some independence. Testing by a peer, another developer on the same team. Then you get to high independence, testing by a formal, separate test team within the same company. And at the very top is very high independence, testing by someone from outside the organization entirely, like a consultant or an auditor.
For the exam, we need to know the benefits, but also the drawbacks. What's the main upside?
The main benefit is effectiveness. Independent testers simply find different kinds of bugs. They challenge assumptions that the development team takes for granted.
Okay, but I can already hear the project manager saying, but that's slow, they don't know the system.
And that is the core drawback. Independence is not a replacement for familiarity. A developer can find and fix many simple bugs in their own code incredibly quickly because they know it inside and out. An independent tester has a learning curve.
So the real-world answer, and probably what's tested in scenarios, is that you need a mix.
Absolutely. The best practice is to use multiple levels of independence. Let developers do their own component testing. It's fast and efficient. Have an independent team do system testing. They'll find the integration issues. And let the actual business users do acceptance testing. They have the highest independence and focus only on whether it meets their needs. It's about getting the best of all worlds.
We have covered a massive amount of ground. That was a thorough deep dive into Chapter 1. Let's do a really quick, rapid recall to lock in these key distinctions.
Okay, listener, try to answer these in your head. First, testing versus debugging.
Testing finds the problem, debugging fixes it.
Good. Verification versus validation.
Verification is building the product right. Validation is building the right product.
Perfect. Quality assurance versus quality control.
QA is process-focused and preventive. QC, which includes testing, is product-focused and corrective.
Excellent. And the EDF chain.
A human error creates a defect in the code, and when that code is executed, it can cause a failure.
You've got it. Knowing these cold is going to be crucial. Let's try 5 exam-style questions to see how you do under pressure.
All right, get ready. Question 1. A tester is currently identifying all the necessary input values and expected results for a specific business requirement. Which phase of the test process is this activity primarily associated with, and what is the key test word generated? A, test implementation, generating test procedures. B, test execution, generating test logs. C, test analysis, generating test conditions. D, test design, generating test cases.
Okay, the correct answer is D, test design, generating test cases.
Why is that the right one?
Because identifying specific inputs and expected results is the very definition of creating a test case. That happens in the test design phase, which is all about figuring out how to test. Test analysis just identifies the high-level conditions, the what to test.
Right. Okay, question 2. A development team uses a highly independent test team to challenge the fundamental assumptions made about the user interface design. This practice is most directly supported by which pair of concepts? A, defects clustering and early testing. B, independence of testing and verification. C, absence of defects fallacy and exhaustive testing. D, independence of testing and constructive communication.
The correct answer here is B, independence of testing and verification.
Unpack that for us.
Well, using an independent team is obviously about the benefits of independence. And the act of challenging assumptions about the design to make sure it's correct is a form of verification. Are we building the system right, according to our understanding?
Okay, I see. Question 3. During a code review, a security expert identifies a buffer overflow vulnerability in a module. This could potentially be exploited, but no failure has actually happened yet. The buffer overflow vulnerability itself is best classified as which of the following? A, error. B, defect. C, failure. D, root cause.
The answer is B, defect.
Why not a failure?
Because the code hasn't been executed, so nothing has failed. The vulnerability is the flaw sitting there in the source code. It's the result of a human error, and it is a defect.
Got it. Question 4. The test manager notices a consistent pattern where tests related to data persistence frequently fail. They recommend updating the company's engineering guidelines for all new projects. This recommendation falls under the domain of A. Quality control, QC. B. Test execution. C. Quality assurance, QA. D. Test planning.
That is a classic example of C quality assurance QA.
Right, because it's about the process.
Exactly. QA is process-oriented and preventive. Using test results to find a weakness in the process like outdated guidelines, and then fixing that process to prevent future bugs is pure quality assurance.
Yeah. Okay, last one. Question 5. Which of the following describes the primary value of establishing traceability between requirements and test cases? A. Proving the absence of defects prior to release. B. Justifying the necessity of debugging activities. C. Evaluating test coverage against the defined test basis. D. Ensuring test execution is completed before the exit criteria are met.
The correct answer is C. Evaluating test coverage against the defined test basis.
And the reasoning.
Traceability's main job is to connect the requirements to the tests. This allows you to measure your coverage and prove that you have tested what you set out to test. Option A is impossible because of Principle 1, and the others confuse traceability with different activities.
And that brings us to the end of our first massive deep dive. We have covered the entire foundational landscape of Chapter 1. You should now have that solid K1 vocabulary and, more importantly, the K2 conceptual understanding to really start your CTFL prep.
You now understand that testing is a strategic activity. It's about risk mitigation, it's about communication, and it's all guided by those 7 core principles.
We spent a lot of time talking about the principle of context dependence and the need for early testing, and that realization that the environment dictates the rules, that leads us perfectly into our next chapter.
It does, because that environment is defined by the software development lifecycle you choose. So our next deep dive will tackle Chapter 2, testing throughout the SDLC. We'll look at how testing changes completely between sequential models, like the V model, and modern iterative and agile models. We'll introduce the critical concept of test levels component, integration, system, and acceptance. This is where you'll see exactly why the process you choose governs everything about how you test.
So review these fundamentals, make sure you know your EDF chain and your 7 principles, and get ready to dive deep into the SDLC in our next session. We'll see you soon.